Okay, let's get started. So today the topic for discussion is multi-arm bandit, and those of you who are interested in this topic, please consider enrolling in ECE 8101 next semester, because that entire class is the entire course is about multi-arm bandits from start to finish. So my goal today is to introduce you to this concept of multi-arm bandit, do an advertisement for ECE 8101, and to give you some broad ideas about how people think about multi-arm bandit, and we'll talk about it in the next class as well, to give you an idea about how people tend to solve multi-arm bandit without going into the proofs of specific results, because those proofs will be covered in ECE 8101 next semester. Okay. So I have 2-3 problems I want to start with. Problem number 1 is, I am a CEO of a research company and I have n different research projects going on. And I only have option to pursue one research project at a time. So this month I'm going to pursue one specific research. If it works, great. If it doesn't work, then next month I'm going to try out some other research project. So I have n research projects. I have to allocate my resources into only one of these research projects. And then after that, I'll make a decision at the next time step whether or not to pursue the same research project or switch to some other research project. The second problem is, so what's the property of this? So if I'm not working on a research project, I'm not really making a progress on the research project, right? There's no papers being written, there's no science being created or understood. So in some sense, if I don't work on a project, the state of the project remains the same. The state of the project is not going to transition. The second problem is, in the medical field, I have n drugs to administer to the patient, and at every point of time, if I am giving a specific drug, the state is going to transition according to that, the transition related to that particular drug. But if I have n different patients and I'm not giving a specific drug to the patient, then the patient will still transition. The state of the patient will still transition. And in these cases, if you're not giving a specific drug, then the state will still transition for that specific health condition, irrespective of so depending on whether you are administering the drug or not administering the drug, the state is going to transition according to different transition kernels. And the third problem is website layout. So you create your new startup, you created the new Facebook or new Google or whatever, and you want to figure out what's the best layout for your website is, or what the best color combination, or what the best information display to the customers are going to look like. And in those cases, what is really happening is you have new customers coming in every day, and they are coming to your website, they are interacting with your website, and your goal is to make sure that the customers keep coming back to your website. Okay, so given a layout, so if you have a specific layout, you know that most number of customers will come back to you. But if you have a bad layout, then none of the customers will come back to you. So your goal is to figure out which one is the best layout for your specific website. Okay, so these are the 3 problems I want you to keep in mind. In problem number 1, if you pick a specific research project, then no progress is going to happen in other research project. In situation number 2, you have different, so whether or not you are taking an action, it just changes the transition kernel of the system. but the state still transitions. Yeah.
So in the first case, it seems like there's n different states.
That's right. There are n
In the
different.
second case, if there's a single patient, there's only one state.
Right. So it's not really the best
you're
example. Yeah.
each drug.
You might have multiple underlying.
So it's almost like the first.
It's almost like a first, yeah. So I'm going to introduce the theoretical framework where you have n separate processes going on.
So what's the difference between the first and second?
In the second one, the state is still transitioning. Even if you don't, like, let's say you have a headache and you have stomach ache, and I'm not treating the headache, but I'm giving you a drug for stomach ache, your headache will still transition to the next state, irrespective of whether or not I provide. You have, yeah.
And you can only give a drug to one.
That's right, yeah. Yeah. And the third one is you have IID transition. So you have new customers are arriving every day and interacting with your website, and you want to figure out the best website layout. Okay, so this class of problems were studied in 1974 to 79. Well, of course, the history of these problems are pretty old, but the main results appeared in this particular era. This one, 1980s, maybe 88, 1992. And this one is 2000, 1952, 1985, and 2000 plus. And the reason why this thing became important, like out of these three different topics, this one was the one that has the maximum societal impact because of the dot-com boom and because of the startups that came out post 2000. Okay, not that these two are not important. I think this one has been used, this sort of idea has been used in wireless systems quite a lot. Like I've seen a lot of papers since 2000 on the second case where you have multiple processes going on and the state is still transitioning. This one I really haven't seen much work recently outside of some academic projects here and there. So I'm not quite sure what happened to the theory that was developed for this class of problems. But anyways, it's important to know the history.
So for the third case, how many states are there?
Here, it's a bit complicated. So you again have the same, the theoretical, the model is going to be the same, and I'm going to introduce the model right now, but the constraints are going to be different. And there will be some minor differences in the model. So let me just get into the model and then maybe we can revisit the problem.
How did we have websites in 1952 and 1985?
I have no idea. I think the person who studied it in 1952 wrote a paper on it, and then he wrote another paper with another PhD student in 1985. Yeah.
This is the theory, not the application.
Right. So remember, in 1950s, there was a lot of work in stochastic approximation. So this was, how do you use simulations to accomplish certain tasks? So that was the era that people were looking at that point of time. Okay, so what's the theoretical model? So I have a family of n bandit processes. I have a family of n bandit processes. My state space S is S1 cross Sn. My UT 0, 1 raised to n. And my state transition IT k IT plus 1 k given ITK UTK. So state transition is basically independent across states. I mean across the n bandits. So the state evolves independent of other bandit process. So this is the state evolution of the kth bandit, and the state evolution of the kth bandit is dependent on the action on the kth bandit, but it doesn't depend on other bandit processes. Yes.
So you, I mean, I don't understand it's like for in processes, and for each one process, it only have two actions, 0 and 1.
You have only two actions, 0 and 1.
Okay.
So either you are going to pull that arm or you're not going to pull that arm. Okay, and then the state is going to evolve depending on the different assumptions. The state is going to evolve in different fashion. Yes.
The T here is the update state, right?
The time update, yeah. And K is the bandit. Like there are n bandits, so K goes from 0 to n, 1 to n. Yeah, so K 1 to n. Okay. So let's look at Gittins and Jones. (1974). So here the state transition is as follows. So UT K is freezing, continuation. So this is 0, this is 1. So they call it freezing and continuation action. And what happens is, if UTK equals to 0, then IT plus 1K equals to ITK. UTK equals to 1 implies ITK plus 1 given ITK1 is known. So in the case of freezing, you have frozen the state, so the state doesn't evolve. If you have allowed the state to evolve, if you're using continuation action, then the state is going to evolve according to a known transition kernel. Another assumption here is that summation of UTK, K goes from 1 to n, is equal to 1 for all t. So you can only pick one action at one arm at a time. You can pull, this is saying pull one arm at a time. Okay, any questions so far?
What is the reward?
The reward is a function of just the state. So the reward here, good question. So I know that so far we were talking about cost, but now we are talking about multi-arm bandit. So in this particular literature, everyone talks about reward. So the reward here is a function R, which is a function of IT and UT. But it's really because you're only picking one action at a time. It's basically a function of the state of that particular ITK, UTK. Yeah, maybe that's not the right way to write it, but this only depends on the arm that was pulled at specific time. So ITK for UTK equals to 1. So for whichever arm that you pulled at that specific time, the reward is a function of that specific state. Yeah.
So
No, the reward is not dependent on the future. The reward still depends on the current state, but it only depends on the state of the arm that you actually pulled. So if you worked on a research project 1 and you wrote a paper on that particular project, then you get the reward. But for other projects that you had shelved, you did not work on it, you don't have any papers coming out of it, so those rewards are 0.
So if you take action 0, then it will do some harm to the process.
No, if you take state equal, if your action is equal to 0, then the state doesn't transition. But you also don't get the reward. Okay? The state doesn't transition, but you don't get the reward. The second one is Whittle. This is 1988. And then I think Weber, 1992. Here the assumptions are as follows. Oh, and we are also looking at discounted. So this is discounted reward problem. Let me write it discounted here. So most of the people are studying discounted reward in the case of this Gittins type of model. This one is average reward. This is average reward. We again have the transition kernel P, I t plus 1, t plus 1, k given I t k 0. And we have it plus 1k given itk1. So depending on whether you are taking action 0 or action 1, you have different transition kernels. And those transition kernels are distinct. We have two types of problem statements here. One is summation of utk k equals 1 to n equals to m, or alternatively summation of k equals 1 to n expected value of this is known as a restless. Okay, so this is a restless bandit setting. What restless means that even if you don't take an action, even if you don't pull that particular arm, the state still transitions. So that's the restless part. It's a bandit because the evolution of the kth bandit doesn't depend on other bandits, other bandit processes. And the second constraint here is instead of having only one action at a time, you can pull only one arm at a time. Here you can pull either M arm at a time or on an average M arm at a time. Okay.
So it means we should pull exactly M arms at a time.
Yeah.
Maybe
So
less than arm.
this one is exactly M at all times. Exactly M. Okay. This one says that on an average you need to have M arms. So maybe this time you do M minus 1, next time you do M plus 2, but subsequent time you need to do M minus 2 and so on and so forth, so that on an average you are pulling M arms at every time. Okay, the third one is Robbins 1952, Lai and Robbins 1985, and a whole bunch of papers 2001 onwards. Actually, I shouldn't say 2000. There was a lot of work done on all these three bandit processes in 1990s. So even though I'm not writing 1990s, but a lot of good paper, a lot of sophisticated papers came out in 1990s. It's just that uh, these are sort of the first papers that came out. Therefore, people study them, and this has a lot of commercial applications, so people study them. What happened in 1990s was good for building the commercial applications 2000 onwards. Okay, so here the idea is itk t equals 1 to infinity or t equals 0 to infinity are IID with PDF probability density function f of r theta. Okay, maybe I shouldn't say with PDF. We'll define what the PDF is. PDF's parameterized by theta. We'll talk about it in a bit. Summation of UTK equals to 1. So this is one arm that you can pull at a time. And the reward is a function of ITK, ITUT equals to RTK for UTK equals to 1. I'm not being very precise here, but basically if the arm that you pull, you get a reward from that particular arm, and for others, you don't get any reward. The arms that you did not pull, you do not get any rewards from them. Okay, so if you have a specific layout of your, so layout is what your state is. No, so layout is not the state. Action is your layout, the layout that you picked, and then you want to see what the reward you're getting out of the specific layout that you have picked. Okay, so but you can only get one reward. You don't get reward for layouts that you did not pick at that particular point of time. Okay, so these are the different classes of bandits. I did cover this particular bandit in my previous offering of reinforcement learning, but I'm not going to do it here. So this one and this one, I'm going to not talk about it. This is the only thing that I'm going to talk about it because there are lots of papers written on it in the recent past. But the reason why I wanted to write these things is because I know people are coming from different backgrounds, and it's not necessary that this is the only one that might be beneficial to them. Maybe this model is beneficial to them or this model is beneficial to them. So you can go to appropriate references and look up for the appropriate theory from those references. Any questions so far? Yes.
The last one is very different because the state evolves independently of the action.
That's right, because in platform, in the sort of web domain, you have different customers coming in at different points of time. So we are not, so this is not talking about personalization. I think personalization was a big push 2010 onwards, but between 2000 to 2010, nobody cared about personalization. So they didn't think of you as an individual. They thought of you as a customer who's coming to the website, browsing some things and then going away. And they treated you as an IID in an IID fashion. Of course, that wasn't the case, but it's good to get started with an IID assumption and then move on to a personalized assumption. Okay, any other question? Yes.
So except for those for the second one, which asks the expectation is M, I think all these three can be treated in the general MDPOI or framework. So why study them separately?
Because the solutions are much easier here. So let me talk about the solution. Okay, so we talked about the state space, the action space, the constraints on the action space. So let's say let me talk about the complexity of this particular thing. So remember that my policy is a function from state to action. So I have the set of actions is n. In the case of the summation of utk equals to 1, so I can only pick one of the arms. So therefore, I have n actions. And what about the state space? So let's say each of this sk was 0 and 1. Then the state space is 2 raised to n. And so the number of policies is n raised to 2 raised to n. Okay, so that's the number of policies, and you want to find the best policy. So you have to do search over these many potential policies. Okay, so if your n is equal to 10 and you only have two states, remember you could have problems where you have multiple states, right? So I'm just picking two states here. So if your n is equal to 10, so this is 10 raised to 1000. That's the complexity of the policy space. Those are the number of policies that are there in these problem statements. Okay, so that gives you a rough idea. It's the exact number of policies for this, especially when you have only two possible states for every bandit process. Now, okay. So this is extremely large number, and you want to do an optimization of these problem statements over this particular large number. So these are the number of policies. So it's a very complicated process. So we want to be able to solve this particular problem. So that's what people were working on for a very long time. And then finally the breakthrough came in the Gittins and Jones paper. And what's that breakthrough? Instead of looking for policies of this type, there is a very specific structure in the problem, right? So the state is not evolving, and the states of different bandits are evolving independently of each other. So there is a lot of structure in this problem. And the question is, can we exploit that structure in order to reduce the search of policies to a more restricted space? And it turns out that that was the case. And they came up with what is known as index policy. So let me introduce what does index policy mean. So I'm going to erase this part. So this is coming from this particular paper, index policy. So what is the index policy? I'm going to define an index of the kth arm based on the state at that particular point of time. So this is some number, so something in R. So this is the index of the kth bandit given the state is itk. So at every state, so this index is a function from sk to R. And at every point of time, the policy, the optimal policy, is of the form pick the arm with highest index. So at every point of time, you look at the states of the system and you identify, you compute what the index of each of those n bandits are based on the state of the n bandit, and then you pick the arm with the highest index. So what do you actually do? Like for PhD students, you look at n different research projects that you are currently working on. Maybe it's 2, maybe it's 3. And then there is a conference deadline or a journal deadline or a special issue deadline, right? So typically the deadline indicates what the index is of a specific arm. So you work on a project whose deadline is nearer. You finish the project before the deadline, you pick the arm with the highest index, and then after that you move on to the next arm with the highest index, which is the next research project for which there is a conference deadline or a journal deadline. Okay, so that's something that's akin to an index policy. So based on the state, you compute the index and then you pick the arm with the highest index. In the case of the second problem, you pick the arm with m highest index, or you pick the arm with index greater than equal to some threshold. In the case of the second project, the restless bandit case, so this is the restless bandit case. This index policy is suboptimal. Okay, so the index policy is known to be suboptimal, but still better than the optimal policy that requires incredible amount of effort and incredible amount of computation. So you don't want to go through the computation. You come up with an index policy, and then you apply that index policy. So in this case, index policy is optimal. So this is the Gittins model. So index policy is optimal. So that was the main result of the Gittins and Jones paper, that instead of looking for policy in this space, I'm going to look for an index policy, and they showed that the index policy, you can come up with an index function such that the index policy is optimal. And remember that the index for the kth arm depends only on the state of the kth arm. So that was the cool factor at that point of time, and because of which the index policy became, there was a gold rush to find index policies for all kinds of bandit problems. So that's when the Whittle and Weber paper, they started looking into this, and then they realized that actually for restless bandit there is no index policy. But then people studied it further, and then they said, okay, you can come up with an index policy which is suboptimal. And then there was a whole bunch of papers that came out on the suboptimality bounds and how suboptimal it is, and can we improve those things, and what kind of problems are indexable, so what assumptions can we make on the state evolution and so on in order to make it indexable, which means that you can have an index policy that is optimal. So a lot of work happened, and we are not going to talk about any of that work here, but there is a whole bunch of papers in 1990s that talks about indexability of different types of bandit processes. Okay, so is the idea of index policy clear? So you look at the kth bandit, you compute the index, and then you pull the arm, you pick the action with the highest index. Okay, that's the idea in the bandit algorithms. Any question? Yes.
So the index policy is simply greedy to the current.
Greedy with respect to the index.
So just pick the largest current reward. So the index corresponding to the largest reward.
I wouldn't call it largest reward, because these are discounted infinite horizon problems. So you look at the value function of different states, potential states, and then you pick the. I think the greedy has a very specific connotation in the reinforcement learning community. So I'm not sure whether you're referring to the same greedy or not, but I don't think you should confuse this with the greedy policy that people talk about in reinforcement learning. Okay.
The reward function should be known, right?
Yeah, in this case, this is all with known models. So everything is known about it. Okay, so everything is known about it. We haven't talked about the Lie and Robbins thing. So we'll talk about it in a bit, which is where the reinforcement learning part comes in. But for these cases, everything is known. So therefore, you can define this index function. It's also difficult, computationally difficult to compute. But compared to this, it is computationally much more efficient. Okay. All right. So we all understand the index policy. So let's talk about Lie and Robbins' paper from 1985. What exactly is their setting? So again, I'm not talking about the Gittins index and Whittle index. Okay, so let's talk about Lai and Robbins 1985. So what is the setting? So so I'm going to pick UTK equals to 1. Then I get reward RTK, which is some function of ITK. I don't make any assumption because ITKs are IIDs, so I can just say that this small RTKs are IIDs. So this ITK are IID implies RTK are IIDs as well. So we'll just talk about the reward distribution. We will not talk about the state evolution part in this particular case. By the way, this was a big confusion in my head when I was reading Lai and Robbins' paper as to where is the state. But then I realized that you don't really need to worry about the state evolution, because if the state is IID, then of course the rewards are IID and we can just work with the distribution of the reward. So RTK has PDF F R theta k. Theta 1 to theta k belongs to a parameter set. So you can have things like I get an exponentially distributed reward with the parameter theta 1 or theta 2 or theta 3 or theta n. Theta n. Okay. I'm going to define m theta k as integral of r fr theta k nu dr minus infinity to infinity. So this is my expected reward. Nu is the base measure with respect to which you are defining the PDF. So for those of you who have not taken measure theory, just think of it as the usual. This is R times the distribution times dr. Okay. Okay. We are in the average reward setting here. But let's truncate the time horizon at time capital T. I'm trying to think about how to introduce the setting here. So let's say I want to maximize the total reward. We are looking at an infinite horizon problem, but there is no total reward here. So I'll switch between average reward. So average reward for the infinite horizon. However, when I'm in a finite horizon setting, so I know that I have to make a decision at every time t. I'm going to look at the total cost, total reward, sorry. until time t. Total reward until time t is expected value of summation t equals 0 to t minus 1 rtk. Can someone tell me what is this expected value? Okay, so I have not introduced a notation, so let me call tk of t is number of times arm k was pulled until between t equals to 0 to no and between time 0 to k minus 1, sorry, t minus 1. Okay, so t is a specific time, small t is a specific time. I'm going to say that before that time, so until t minus 1, how many times I have pulled arm k, I'm going to denote it by this number tk of t. So what is this summation of reward until time t minus 1? This is m theta k times tk of capital T summation over k equals 1 to n. That's the total reward that I have accrued until expected reward, total expected reward until time capital T. So this is the reward that I have accrued, expected reward that I have accrued until capital time T. Okay. Any questions so far?
I'm a little confused.
Yes.
For the equation, the left side seems to be a function of k, on the right is not.
That's right, but good point. But you are only picking one k at a time. So let me just sum over all k equals 1 to n as well. But remember that most of the k's are, I mean, all the k's except the one that you picked is 0. So in some sense, they don't really add much. Okay, you are only picking one action. So one k is non-zero, and that's the k I'm considering here. But anyways, for completeness, let's add k goes from 1 to n as well. Any other question? All of you agree with this? All of you agree with this? Everybody's okay with this expression? Okay. Yes.
Yes, um, so like somehow is there sort of a mean, is this the mean number of times arm k?
Yes, m theta k is the mean.
No, but that's the mean value, but then like the number of times it was pulled also seems to involve a mean.
Oh yeah, oh that's right. Thank you so much for pointing that out. You are right. There is an expected value of tk of t. Thank you. Okay. Any other? Yes.
Expected value by summation, right? That expected value,
This one. Yeah, that's the expected value.
I'm saying like that's the summation of the mean times the expected value.
Correct. That's right. Summation of mean times the expected value. Okay. So the question here, so let's get to the multi-arm bandit, the reinforcement learning side of things. So in reinforcement learning, our assumption is we don't know anything about the distribution. So if I knew about the distribution, I'll always pick the arm with the maximum mean reward in this particular case. So therefore, for k, which is the optimal, k which has the maximum mean reward, this will be capital T, and for other arms that are non-optimal, this would be equal to 0, and this would be the maximum reward that you can get out of the k arms. So that would be the case if I knew all the distribution. Now the problem in this particular setting is I don't know the distribution. So what I mean is I know this PDF function as a function of theta, but I don't know theta 1 to theta n. All I know is the parameter set in which theta 1 to theta n lies. So what is the setting now in Lie and Robbins? So theta is known, theta 1 to theta n not known. Okay, so I know the parameter set. I know that, and then f of r theta is known. So the functional form is known. What function, what kind of distribution function it is, that part is known. But I don't know theta 1 to theta n. So I don't know what the parameter for the PDF looks like for all these n arms. So let's look at an example of this setting. So everybody came to Columbus on day 1 and they don't know where they want to do grocery shopping. Okay. And you learned from people that there are 3 places where you can do grocery shopping. One is Kroger, one is Giant Eagle, one is Whole Foods. Okay. And now you need to figure out which one has the best fruits, vegetables, meat, whatever you want to eat at the best prices, right? So ultimately your goal is to minimize your cost of groceries while getting the quality that you want. So on day 1, I don't know what the distribution of the cost of groceries is going to look like for what I'm going to eat. Okay. So put yourself in your shoes on day 1 at Columbus. What would you do? How would you go about figuring out where you want to go for grocery shopping? So every day you have to go, you have to get some groceries and you have to cook food and you have to eat. So you have to do it day in, day out. Every day you have to do this. So what would your algorithm be for figuring out where to shop from on day 1 in Columbus? Yes.
Is it random?
Choose at random. Okay. So one option is choose randomly. So what happens after time capital T? How many times have you gone to Kroger? T over 3. How many times have you gone to Whole Foods? T over 3. How many times have you gone to Giant Eagle? Capital T over 3. That's roughly the expected value in the long run. So option one is to choose randomly. Anything else that you can do? Sorry? There is no simulator. You have to walk to the grocery store. Yes. Based on distance, not quite the answer I was looking for, but okay. Based on distance. Anything else? Anyone else has a better algorithm?
Based on experience of others.
Okay, so you have an experience. So what happens? So how do you go about picking the right place for you to shop?
Maybe experience of others.
Experience of others. Okay, that's a good idea. Okay, third, experience of others. This would become important in the next class. Okay, so I'll get to it in a bit. Anything else? So I guess the algorithm that you are talking about is you ask someone else which one do you shop from. They said Kroger, then you go to Kroger every day, and you don't switch. You don't figure out what's there in Whole Foods and what's there in Giant Eagle ever, right? So that's one strategy. You ask others where should I shop from, and then you shop from there forever. You don't go to other places. Anyone else?
We choose one grocery store randomly and day 1, and the second day we keep B compared with day 1, and if it is higher, we choose another. Pick with each time we.
Okay, so instead of choosing randomly, you are initially choosing randomly, and then based on the
Yes, choose the
cost of groceries. Okay,
like
so
the homework one problem, something like that. The house beating homework. The homework one, house option. You always choose the lowest.
Okay.
So it is
Okay. Yeah. Okay. Choose randomly. Accumulate experience of rewards. And then what?
So based on history, I will choose
Okay.
until I run all the grocery stores.
Choose the best option. This is, by the way, this is the case in homework 3. You have to figure out the regret for this particular strategy. But anyways, okay. So this fourth option is I'm going to choose randomly. I'm going to accumulate experience of reward. So maybe Kroger, I paid $10 for the grocery. In Whole Foods, I paid $20 and so on. And after accumulating enough experience, I'm going to choose the best option, which is Kroger is the best for me. I'm only going to go to Kroger, moving on. All right. So it turns out that all of these are somewhat bad strategies to pick groceries. Okay. So what's a good strategy for picking groceries? So that's the question that Lai and Robin asked in 1985. What is a good way to pick groceries? And naturally, you want to optimize the average reward. And in this case, setting if you knew everything about Columbus, if you knew everything about Kroger, Whole Foods, and Giant Eagle, you would pick K star to be the argmax of M theta K equals 1 to N. And then you will always pick the arm that is the best arm, and you will get the total reward capital T times M star. So M star is M theta K star. So this is the total reward you would get if you knew everything. Now I don't know theta 1 to theta n, so this is what I can get in expectation until time capital T. So how do you know if you have a good algorithm, good policy to figure out where to shop from, or you don't have a good policy? So how would you measure? This is the best you can do. This is what you are actually doing. So how would you measure whether your policy is good or bad? This is the best you can do. This is what you are actually doing. Okay. Now you want to measure if your policy is good or bad. How would you do it? So I'm pushing you back to 1985, and you have to come up with a way to measure whether you are doing good or bad. Okay. So they thought about this, and they came up with this notion of regret. I'm not sure if regret was known before that, but they definitely made it pretty famous. So regret is, anyone knows what regret is? I mean, not the reinforcement learning definition, but how do you define regret in life? Has anyone regretted before? I'm sure everyone has. How do you define regret? Anyone knows what regret is? Okay, so regret is the best option, or I should say reward of the best option minus actual reward. If you knew all about the life during PhD, right? So you would have picked the best option, which is whether or not to do PhD. But now because you did not know that, you enrolled yourself into the PhD program, and you're getting the actual reward, which is conference papers, I guess. Right? So that difference between what you could have gotten minus what you are actually getting is regret. Okay? That's the notion of regret in life as well. So they define regret of a policy mu at time t as t times m star minus what is that, summation k equals 1 to n m theta k expected value of Ti capital T. Oh, Tk, right? Yeah, Tk capital T, perfect. And I'm going to write it in a different way. K equals 1 to n m star minus m theta k times expected value of Tk times capital T. So this is my regret. This is the definition of regret that I have. Okay, so let's look at option 1. So policy 1. What is the expected value of Tk capital T? This would be T over n. I'm assuming T is capital T is a very large number. So I'm not assuming capital T is like 5 or 6. I'm thinking of capital T as 1 million. And in that case, this is roughly approximately equal to capital T over n. So what is my regret of this particular policy? It's summation k equals 1 to n m star minus m theta k times T over n, or this is capital O of T. So it's some constant multiplied by capital T. What about option 3? So mu equals to option 3. Expected value of Tk of T. Sorry? So remember, in option 3, you pick whatever is the optimal of your friend. So your friend has done some optimization and he or she figured out that Kroger is the best place for him or her, and then that's the option you're picking.
So it's T to wherever your friend goes, and then 0.
It's 0 for others, right? So in expectation, this would be T over n again, right? Because your friends might have different preferences, and therefore in expectation this is capital T over n, and you get the same regret. Okay, so the regret that whatever policies you have come up with in the class, it seems to me that the regret is order of T. So it's some constant multiplied by capital T. That's the regret that you are accruing over time. Is that a good regret or a bad regret? Okay. Okay, so they ask the following question. So what would be a good policy So they said that a good policy should satisfy this condition. Limit t goes to infinity, regret mu of t over t raised to a equals to 0 for all a greater than 0. That is their notion of a good policy. Okay, so what is the setting here? Let me go back all over to the beginning. So I know the parameter set, I don't know the parameters, I know the functional form of the distribution. I want to come up with a policy to figure out what the best option for me is. So in the case of Facebook, they wanted to figure out what the best layout of the website looks like. In the case of Google, they wanted to figure out what the best advertisements on the website should look like. That was also the case for the New York Times. So at every point of time, people are coming to the website, they are browsing something, I want to get money out of that browsing process. So I don't know what layout is going to bring me the best reward. So therefore, I want to figure out with a policy, I want to come up with a policy that gives me the best reward. Okay, so we came up with some options of how we will come up with the best, how we'll get to the best reward. It turns out that with all those different options, the regret that I'm accruing appears to be order of t, which is some constant multiplied by t. So they needed to come up with a policy. They wanted to figure out what is a good policy. So all the policies that we could come up with without applying too much thought turns out to have regret of O of t. So they said, well, I have a good policy if my regret divided by capital T raised to a for any a greater than 0 should be equal to 0 in this particular limit. So what does this mean? My regret mu of t should be equal to log t or c log t. C is a constant, so c log t, or it could be c log t log t, or it could be c log t raised to 5 or c log t raised to 100 and so on. So these are all possible good regrets. If you can come up with a policy that satisfies these sort of regret, then definitely you are satisfying this, and this seems to be a good policy because all of these regrets satisfy this particular criteria. Okay, so I want to come up with a policy mu which gives me a regret of this type. I'm also going to define the policy mu somewhat rigorously now. So in this case, policy mu would be a collection of mu0, mu1, and so on. Each mu t maps the information at time t to action at time t. So instead of policy mapping state to action, now I have to map the entire information to action. Because remember, in this case, I don't quite know what the distributions are going to look like. So I first have to convert this information into useful variables, useful index. So this information will then need to be mapped to index, and then we need to take the action. So that's what we will be talking about in some time. But roughly here, the policy now is a function of information to action. And the way I'm going to use this information is I'm going to convert it to an index, and then from the index, I'm going to convert it into an action according to the index policy. Okay, so what is information at time t? What all information I have accrued? until time t, it's the reward rt0, ut0, rt1, sorry, r0k, u0k. Well, okay, I'm just going to I want to write R0K, but then I only know the reward from the arm that I have actually pulled, not the arms that I did not pull. So let me just write it in words. So history of rewards until time t. But you also know which arm you pulled. So history of rewards from the arms pulled until time t. So if I pull arm 1, I know what the reward I'm getting. I pulled arm 2, I know the sequence of rewards that I've gotten. Okay. Okay, so here is the update. So I want to figure out a policy mu that maps the information to action such that the regret is satisfying this particular condition. So what is the main result of their paper? So this is the main result that they established, which we will not establish because it was a very complicated result. Well, okay, so what are the two questions? So question 1 that they asked, what is the lower bound on regret? And then question 2 is it achievable? Is the lower bound achievable from some policy mu? So these were the two questions that their papers focused on. What's the lower bound on the regret, and what's a policy that you can construct that achieves that particular lower bound up to some constant. So you don't really have to achieve the lower bound, but you have to achieve up to some constant. You want to achieve this particular lower bound. So the main result for question number 1. Oh, in order to do that, I need to define KL divergence. How many of you are familiar with KL divergence? A few people, okay. So let me introduce KL divergence. I think I'll introduce it here. So KL divergence DKL theta j theta star is defined as minus infinity to infinity log f r theta j over f r theta star f r theta j mu dr. That's the KL divergence. And their theorem is, under certain assumptions, technical assumptions, so there are some mild technical assumptions, so we don't want to get into it, but under some mild technical assumption, if mu satisfies limit t goes to infinity regret mu capital T over t raised to a equals to 0 for all a greater than 0, then lim inf t goes to infinity, regret mu t over log t equals to summation m theta k less than m star Okay, so what they are saying, what the authors are saying in that particular paper is if mu is a good policy for this class of problems, so that's what a good policy is. So if mu is a good policy for this class of problems, then regret divided by log of t asymptotically becomes a constant that depends on, inversely depends on the KL divergence between theta k and theta star. And it depends on the difference of the mean reward, the best mean reward, minus the mean reward of arm k. But I'm not looking at it from, so remember, this is for all cases that m theta k is strictly less than m star. So I'm only looking at arms that are suboptimal. I'm looking at the difference in the reward, expected reward, dividing it by the KL divergence of theta k and theta star. Can you see it in the back? Kind of, sort of? Okay. I wish I could just copy and paste it there, but I can't. Let me write it again. Yes.
So we're optimizing over the mean less than m star, right?
Mean less, I'm not optimizing over, but yeah, so m theta k is less than m star. Yeah.
Then is there ever a possibility there's another better reward than your best reward?
No, then that's the best reward, right? Yeah. So you're only looking at the arms that are suboptimal. So these are the arms that are suboptimal, and the regret divided by log t satisfies this particular condition where t goes to infinity. So what the upshot is that regret is some constant times log t. Okay, where the constant depends on a lot of different things. Okay, so that's the constant that's written here when t is sufficiently large. They also showed the answer to Q2. So their second part of the paper was saying that there exists a policy mu such that it is achievable. Regret mu t is order of log t. Okay, so there exists a policy. They actually constructed a policy that achieves the regret of log t in this class of problems. This paper is an extremely technical paper, so only if you are very mathematically inclined, you should go back and read the paper. It's a very good paper, but it's a paper in statistics journal, so it uses a lot of statistics jargon as well as it's heavy on math. Okay, so not an easy to read paper, but all in all, the key contribution of this particular work, which kind of started this whole field of, I mean, not started, but it blew up during the post-dot-com bubble, was this fact that you can come up with policies where you get the regret, which is order of log t. Now remember, all the options we had on the board, like all the different algorithms that we could come up with, those regrets were order of t. Okay, so coming up with order of log t regret was sort of a gold rush at that point of time in 2000, 1990s and 2000, and a whole bunch of people worked on identifying this policy's muti that maps information to action, which achieves the regret of log t. Okay, and that was the goal of a lot of researchers, a lot of PhD students wrote thesis on identifying these policies where the regret is log t. Any questions so far? Okay, so what have we done so far? We have talked about this multi-arm bandit, class of multi-arm bandit problems, and then we didn't talk about these Gittins model and the restless bandits. We talked about the Lai and Robbins paper, where the setting was that the state evolves in an IID fashion, consequently the reward evolves according to the IID fashion. I don't know the reward model, which means that I don't know the parameter that drives the distribution, but I do know the parameter, the functional form of the PDF of the distribution of the reward. And then they said, okay, what's a good exploration policy? What's a good policy to use in these class of multi-arm bandit problems? And they said that, okay, a good policy should satisfy this particular condition. That's the definition of a good policy. And then they said, okay, under certain technical assumptions, if mu is a good policy, then the regret must be order of log t. Okay, that was the main result. And then there is a policy such that you can achieve the regret, which is order of log t. Now, in the next class, I'm going to talk about a whole bunch of algorithms that people have designed since then, which achieves this particular regret. And the only thing I'm going to do is give you the algorithm, but without going into the proof of what the regret looks like and how did they compute that the regret is log t or not. Some of these proofs are there in my previous offering of reinforcement learning if you're interested. Alternatively, I'll write down the paper so you can go to the papers and look at the regret proof in the papers itself. But that's pretty much it for today. Thank you, and I'll see you on Thursday.